There's a lot of situations in real life that have exponential change patterns. So we've talked about like population growth, spread of a virus. In fact, that whole going viral idea of like a video or something is that the increase in views is following an exponential pattern of change. The thing is, a lot of times in real life, that change is described in terms of percents. Think about a lot of statistics that's described in terms of percents change, not by like the multiplier that's being used in the exponential function, because that's not something that a lot of people understand or relate to. They're not that familiar with it. And so instead of using a growth factor and a multiplier when we're describing this, a lot of times change is described using a percent change. And so we have two things. Now, the multiplier, the repeated multiplier, we call that a factor. If it's a percent change, we call that a rate. And so what we're going to do is just talk about kind of translating between growth factors and growth rates, and decay factors and decay rates, because rates are tend to be what are commonly communicated to people, whereas the multiplier or the factor is what's used to write the equation, the model. So on this one, we're going to, first of all, just kind of revisit the population problem. And it just shows that the way we're calculating, you could calculate the percent change, for example, those rabbits going from 100 to 180 and so, is by comparing one year to the next. And so when it has this n and n plus 1, this is a symbolic way of saying 1 year and the year after it. So if it was year 5 and year 6, you could use the difference between year 5 and year 6, divide it by the year 5 starting number, and you'd have the percent. So you can see here, when we had that population of 100, there's a typo right there. Population of 100 rabbits increasing by 80 rabbits. 80 rabbits coming from 100 rabbits, 80 out of 100 is 0.8, or 80%. And then for the next year, when it went from, year 1 to year 2, from 180 to 324 rabbits, that's 144 rabbits out of 180 that they came from, that's another 80%. And so, like I said, the growth rate, that's a percent, and that's usually how it's reported. But when we're modeling it mathematically with an exponential function, we want a growth factor, a multiplier. And so this is our key question here, not the question you're supposed to be answering right now, but a question we're going to explore in this extension, which is how are the growth rate and the growth factor related to each other? How do you go back and forth between the two? So we're going to approach this by looking at a scenario. So money is a big place where exponential change happens because whether you're investing money in something that increases in value, we call that appreciation, or you buy something that loses value, they call that depreciation. Think about like a car, you buy a new car and then it starts to lose value, that's depreciation. Money is a place where a lot of people are going to be interacting with exponential change, whether they really realize it or not. So we're going to look at a hypothetical stamp that starts out at a value of $2,500 and look at what happens when it goes up by 6% each year. And so that might sound kind of linear, but it isn't. So if we do this, I'm going to show sort of the hard way of doing this first to calculate the new value each year. And then we'll see that knowing that it's not a linear pattern of change, spoiler, that's question number 2, it is not linear, it's exponential. That we can do this the hard way, but if we know how to model this using an exponential function, there is a shortcut. So first we're going to do this the hard way. Let's say we have $2,500, or it has a value of $2,500, and it goes up by 6%. Now remember, 6% as a decimal is 0.06. Move the decimal 2 places to the left. You have the decimal form of that percent. So if we take 2,500 times 0.06, we get 150. Add that to the $2,500 value that it started with, and you have $2,650. $2,650. It went up by $150. And then that value goes up by 6%. So you would do 2,650 times 0.06, which is 159. Add that to 2,650, and you have 2,809. and so on all the way down. It's a little bit tedious, but once you do it a couple times, you can actually calculate these pretty fast. But notice we're going for the first year, the change is 150. The second time, it's 159. That's nonlinear change. It's going up faster the second year than it is the first year. And if you think about it, if you multiply 2809 by 0.06, add on, it's about 168 or $169. It's going up by a larger and larger value each time. And so we've got exponential change. And so knowing that this is exponential change, we could actually look at this table a different way and write an equation for the value of the stamp after X years. So what we could do is what we did with that rabbit population to find the multiplier. So if we know it's going from 2,500 to 2,650, and we know that this is an exponential rate of change, we don't have to do all of this stuff. We could just find our multiplier by doing 2,650 divided by 2,500, and we get 1.06. And if we do the same thing for the next interval, 2809 divided by 2650, you get 1.06, the same multiplier. So we've got our starting value and we've got our multiplier. So now we can write an equation for the value of the stamp after X years. Y equals 2,500, your starting value, times 1.06 to the power of X, where Y is the total value after some number of years and X is the number of years. So if we want to figure out now how long it takes for that stamp to double, so doubling the first time means it's going from 2,500 to 5,000. Doubling the second time is going from 5,000 to 10,000. And this is where we need to go to our calculator and just count how many times we multiply that by 1.06. Twice, 3 times, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So you'll notice the 12th year, it hits 5,000, and then another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That's a total of 24 years. It doubles again to 10,000. So notice, both times it doubled, it took about 12 years to do so. So like I said in the previous one, it would seem like it would take longer for something to increase in value by $5,000 that second time versus $2,500 that first time that it doubles. But remember that exponential curve gets steeper and steeper. So even though it has more money to gain to double, the line is climbing more steeply, so it gains that value in the same amount of time.